So we're covering several sections today, and I'm just going to hit the highlights of sections 4.1 through 4.6. So what we're really doing here is we're modeling solids as being just made up of balls and springs. And these sections are just kind of getting you into that mindset and then describing how springs in series and springs in parallel work. So you don't need to focus quite so much on the mathematics here as the ideas. The main things to get out of this are how springs combine in series and in parallel. And so what you want to ask is, if we have two springs side by side, each with spring constant K, what is the effective spring constant of both of those? In other words, two springs side by side, are those going to act like a stiffer spring or a weaker spring? And you want to ask the same question with two springs that are in series. Each has spring constant K. Do these act like a single spring that has a spring constant larger than K or smaller than K? So those are the things you really want to get out of those sections. Then the next thing you really want to focus on is Young's modulus. In particular, you want to look at the macroscopic version of Young's modulus. This is the primary one we'll be using, although having some familiarity with the microscopic version is not a bad idea. So right here we have the macroscopic Young's modulus. And this term right up here is the stress, force per unit area. In other words, if you put a large force on a small area, you get a large stress. But if you spread that force out over a larger area, the stress is not quite so great. The strain is this term down here. And just think of that, how hard you're stretching something. Delta L, that's the change in length. L is the original length. So you can think of this also as the fractional change in length. And it's going to typically be a fairly small number, because unless you've got something like silly putty or rubber band or whatever, your change in length of your material is not going to be very large compared to the original length. But you can rearrange these terms a little bit like this, which is a little bit more easy to look at. The primary reason that we write it like this is just to separate out the stress and the strain. Now, one thing I want you to do is to kind of relate this equation to our spring equation. And because Young's modulus is really treating the system of a solid object as if it's made out of these ball and spring model. If that's the case, then there's got to be some relation between these two. So what we do is we take Young's modulus here, write that equation down, A times delta L, and I'm going to rearrange this so it looks similar to my spring equation. So I'm going to get force by itself. So let me see, divide by L over A delta L. That gives me F is equal to Y A delta L over L. Now, notice that we got delta L here, delta L here. This term right here is acting like K. Ignore the minus sign for right now, and that's okay. In other words, our effective spring constant from Young's modulus equation is Y A over L. Now, the thing to keep in mind is that area represents springs in parallel, and L represents springs in series. So the larger our area, the more of these atomic springs there are in parallel. The longer our length, the more atomic springs we have in series. And if you compare how we expect the effective spring constant to behave with parallel and series springs, these things are in the correct placement. In other words, when you put springs in parallel, you expect to get a stiffer effective spring constant. When you put springs in series, you expect to get a less strong effective spring constant. So Y is essentially related to the atomic spring constant. Now, it's not exactly equal to it, but another equation for Y is the spring constant for the interatomic spring divided by the distance between those atoms. So very closely related. It's just essentially the atomic spring constant divided by the atomic spacing. And this dependence on atomic spacing explains why in one of the sections we work on how to calculate out that atomic spacing. Now that's not something you're going to need to worry about, but it's at least nice to know where it is and to have a sense as to how large that spacing really is.